Alright, time for another DraftPhysics.com video presentation. Debate physics also. But we cannot provoke too many to participate in an actual debate of actual subjects in physics. So I'm going to do a response video of sorts to a video by something called FloatHeadPhysics. And he's done a few videos on Einstein's different theories of relativity and this E equals mc squared and the speed of light and what rest mass is versus actual mass. And so we'll play some of it, but I guess I'll start by just arguing how I would interpret it, what I think the truth is in terms of how the universe actually works. So as I have said in previous videos, I think there's just two kinds of stuff in the universe. There's the force, and then there's matter. Okay, and the matter is just electrons and protons. The neutron is a composite of these things. Now maybe I'll use colors to help emphasize this at some point, but we'll see. And the force is the only thing that's active, innately, elementally. So the force has all the energy, and it's moving the speed of light. And the idea is that the force pushes the matter. So it's a push universe. All right. Okay, there's no pulls. There's only pushes. And in the absence of a push can look like a pull, but it's not. It's just the absence of a push, and then something else is going to push to fill the void. And so things can be in what can be called some sort of equilibrium. Now the fact is the matter is innately dead. It doesn't have any capacity to move or do anything on its own, and only when it is being pushed by a force can it have the potential to move. So you could argue that the force hits an electron, let's say, and the force is in this quantizable chunks, little quanta of energy, as Einstein would say. And so it can have quite a bit going somewhere, but the truth would be is if I had another electron, okay, and it was going the opposite way with a bunch of force, the electrons, okay, would have a problem getting anywhere because they're going to have force that they're going to repel, and that force would end up being hitting and returning and hitting and returning and hitting and returning and bouncing between the electrons and sort of negating some of that energy. Another way to look at it would be how they describe in physics the strong force, which holds protons together. So you could have two protons, and the argument I would make is that what makes it easy to have two protons get really close to each other is as if you put an electron in between them, okay? Because then the two protons can't see each other. All right, oops, that's an electron. All right. And the argument is that the proton force goes through the electron force goes through the protons. So I really don't really want to explain that again, but I guess I really have to real quick. So if you understand that there's two kinds of force, there's two kinds of matter. So the force bit really has two kinds, electron force and proton force. So if a piece of proton force hits an electron, it goes straight through, and it pops out as an electron force. And then if an electron force goes into a proton, okay, it pops out a proton force. And if a proton force hits a proton, okay, it sticks. If it's not going the opposite way, if it's not moving in this direction yet, in this dimension, then it sticks and it moves it with some percentage of the speed of light. Let's just say 10% for the fun of it. So the force bit is now slowed down, pushing the matter. So now we have what he would call causality. We have the speed of causality, which is really the mechanism that's really causing gravity and everything else. is the fact that when the force is pushing matter, it's not pushing it at the same speed it was going, because the matter has mass and it has to push the extra mass. So it has to go slower than the speed of light. And you can understand, no matter how many of these I piled on, if it's always some kind of 10% number, I can get this going faster and faster, but I can never get it to go faster than the force. I can never even get it to the speed of light, because there's always a little tiny diminishment. So even if I put multiple gamma rays behind an electron, I still can't get it to go the speed of light, because it's still slower then, because there's still matter it has to push, even if it's a tiny percentage that's still not going. You know, it's just one of these, there's infinitely too much mass for it to go the same speed, because there's always more mass to push than what it would push if there was no mass. Obviously, when it's pushing no mass, it goes the speed of light. If it's pushing any amount of mass, it has to go slower than the speed of light. So that's the speed limit problem. So anyway, with these simple rules, and the other rule would be as if there was a bunch of this and a force comes and hits this way, then this piece of force, this little piece bounces off here and this one reflects off here. So if a force hits in the opposite direction, it slows it down by knocking off whatever extra it has in that direction. And so then you can understand that in this situation, you could have two protons that have an awful lot of force. Okay, and if you have this kind of a mechanism between them, an electron, there's no way for any red force to come this way. None can get from here through the electron to this other proton. So there can't be any, I can't make one go this way and then hit the proton this way. There's no way to hit this proton with any red force coming from this way. There's no way to hit that one with any red force coming from that way. So you can understand there's no way to get rid of this extra energy, okay, until the protons shift or move. If one of these is moved and they can start seeing each other, then they can start reflecting off of each other. All right, but otherwise, no luck. See, I mean, if there were off-centered a little, say this proton moved over here, then you could see that an electron force could go in here and it would turn into a proton force here, and it could hit the proton then, okay, and the proton could lose some of its momentum. So it just depends on how much it fluctuates, how much energy it can lose. But if it stays really stable, it can maintain a huge amount of energy. So I guess what the argument I would make is that the concept of rest for matter inside of the nucleuses of atoms is that they contain a lot of that force material. So you could argue that inside the nucleus there's a bunch of electrons and protons and arrangements, and for simplicity, let me just make it, we'll just deal with electron force for this example, even though the proton force is the dominant force inside the nucleus. There's no real, there's no real good reason I probably should just do it. Let me just do it this way with an electron, and we'll do protons, because that's more honest to the problem inside a nucleus. There's twice as many protons as there are electrons in the nucleus, because the electrons are in the nucleus through the existence of the neutrons. So if it wasn't for the neutrons, there wouldn't be any electrons in the nucleus, but the neutron is an electron and a proton. That would be my argument. So I could understand, let's just make the geometry really simple. So we have 4 protons and 1 electron. You could understand that each one of these protons could have energy pushing them in. All right. And then there's energy, because they can see each other here. There's energy here that can push, hits them and causes some of these reflections and balances. So they have energy going this way and this way, all 4 of these directions. All right. And then they have the complete deficit when they look at the electron. So from every perspective, the electron can only radiate black force, because any red force that goes in comes out black. So you can sort of understand that the proton can't see anything repulsive from the electron, and it certainly can't see anything repulsive from the proton on this opposite side. So it can only see these protons as producing pressure against any energy they have. So I would argue that the balance is created. The reason why these nucleuses are created inside of suns is because the pressure, the heat's very high. And in this high heat environment, everything's moving really fast. So everything's being pushed. The electrons and protons in the plasma, or whatever you want to call it, they have very high velocities. And they're being put into arrangements, and it just happens, they happen to push into these arrangements in just the right way, and they sort of get locked in them. So once they're in a relationship, they're attracted to the electron, and they're repelled by the other proton. So they can't really go in further, and they can't go out, and so they're sort of stuck in a position, and that geometry becomes very secure. And what you're really saying is basically there's 100 or so geometric configurations that you can make that will survive outside of the sun. All right, where all of this pressure is still exists, all of this pressure is still pushing the protons. These protons are full of energy. They got a lot of energy pushing, but there's all this other energy pushing them away from each other. So they're locked in a position where they can't get anywhere, and they're balanced, but they have maintained all of this extra energy. So this would be the rest mass of the rest energy of a nucleus is going to be a lot different than, say, just a proton alone in space. And that's why if you break these atoms, these nucleuses, you release a whole bunch of energy, is because it's already under high pressure. So if anything happens to disrupt this geometry and the proton moves over here, for example, then all of a sudden now it could shoot right out of the atom or shoot right through the atom because it has a whole bunch of stored pressure, and the whole thing starts to break apart, and then these electrons and protons will fly out of the nucleus at very high speeds because they have collected, they retain a whole bunch of pressure they got inside the core of a sun. So they gained all of this huge amount of pressure when they were invented, okay, when they were built inside the pressure cooker, the high pressure of a sun. So that's why they have what you could call rest mass, all right, and rest energy, is because they can release an awful lot of velocity because of this stored force. Yeah, okay. I just don't know if I'm satisfied with which direction I wanted to go with this video, but we'll see. Pause for a moment. Alright, so what I wanted to start with is just the idea that it's a push universe, that the force is completely separate and different than the matter. The force has all the motion, and it actually has to be attached to the matter. It has to be occupied pushing matter, okay, or it's free in the universe. It's all in two forms. It's either in some sort of photonic type energy moving through the universe, or it's pushing an electron or a proton. And those two states mean that there can be a circumstance, okay, as stated here, if a photons travel slower than c. The photons never travel slower than c. But to get through matter, they have to push electrons and protons. And when they're pushing electrons and protons, they won't be going the speed of light anymore because they're pushing a weight. A Sisyphus is in their way, a Sisyphus boulder. And so when they're pushing an electron, they're greatly diminished in how much speed they have. And it's the faster they can get the electron to go, the less energy they're losing, so to speak, less time they're losing. But if it's just, say, one force bit hits an electron and it's only going 10% the speed of light, you can understand that's a substantial reduction in its progress in the universe. That piece of force isn't getting where it would have been if it wasn't pushing the matter. All right, so now we'll go back to the beginning, and maybe we'll play some of this.
One simple but
maybe I should just download it. Way too many commercials, unfortunately. All right, should be back. The downside is I can't see what's the different places might be saying, so we just have to go for broke.
Equals mc squared. So I thought that photons' energy can be converted into mass, and so therefore they should have mass given by E by c squared. But what I read and heard from everyone is that that's wrong. Photons are massless.
All right, so obviously they have momentum, and that's what Einstein argued. So obviously they have some sort of mass, to have momentum. So you can't really argue the argument in any reasonable sense that we know they convey what we end up calling momentum. So it's kind of silly not to say they don't have any mass component that makes it possible for them to convey energy, but it really doesn't matter, because the point is they're the only source of motion. So the matter doesn't have any energy until a piece of this force stuff is sticking to it. All right, that's what I would argue. It has to be pushed. Matter has to be pushed. It can't be just hit. It has to be continually pushed. The force has to stay with it for it to keep moving. If the force isn't still stuck to it, it doesn't keep moving. It has to collect force to move. And the more force it collects, the faster it moves. And again, that only goes for the electrons and the protons, which are affected by drag. Okay, so he says E doesn't apply to photons, but the argument would be is because he's saying that there's this distinction between two kinds of energy, rest energy. So let me go to the part where he uses the example of a tennis ball. This is the part, okay. So here he's arguing that if you add up the mass of our electrons and protons, they don't equal but 1% of our weight. Okay, but that's not true, because those calculations are all based on the kinetic energy formula. So they're obviously measure the mass of the electron by saying, here we gave it a certain amount of energy, and based on that energy it has a certain velocity, and then they're squaring the velocity. So obviously, because of the squared velocity term, the mass term goes way down. So the mass's contribution to the energy becomes almost non-existent, because the energy component, the v squared, is such a big percentage. But if they actually measured it by momentum, that is, they took the momentum of an electron without the v squared, then the mass would go way up. And so then you would be able to account for our weight by the weight of our electrons and protons. So I think this was sort of just not true. Okay, so here he's saying mass, amount of stuff. It's not the amount of stuff. And I would argue that certainly you can measure it as the amount of stuff, because that's what it is. Now, whether energy is mass, I would argue no, of course energy is not mass. And Einstein's basically saying, when he's talking about how much energy matter has, he's talking about matter in the form of atomic nucleuses. So it's not how much energy an electron has or how much energy a proton has, which we know is always variable. I can give them any amount of energy. There's no standard amount of energy. And the point is that the average state that the matter's in, okay, is in these atomic states, and they have a certain average amount of energy. But it's certainly not mc squared. That's just playing with big numbers. So again, this is more argument that we don't add up, the electrons and protons don't add up to our weight. And I would argue that yes, they would, if you weren't using the silly kinetic energy formula to determine the weight. All right, and then he said something about Einstein said it's the Higgs field, when obviously the Higgs field didn't have anything to do with Einstein. So I thought that was really cheating. I guess the part I want is further down still. All right, so here's the example he's using. A spring, you compress a spring, you know there's energy in the compression of the spring. But if a tennis ball is moving in one direction, there's no stored energy in the tennis ball itself. It's not a compressed spring. I mean, it's actively moving, okay, which you have to account for, I would argue. But this is almost like the heat argument. You know, heat is the potential to give radiation away in all directions. And you could almost argue that if I could make heat go in one direction, like a laser beam, like a regular light versus a laser beam, then it's the same thing. You basically have heat in a direction when you're moving. So it's the same thing as heat, or potential, because you've actually got energy in one direction. You have mass in the direction you're moving. You really don't have mass, you know, you don't weigh anything in the direction you're not moving. So if I put something on a scale, it's only moving in one direction. The scale can read. If I put the scale here, it doesn't weigh anything. Put the scale above, it doesn't weigh anything. Put the scale on the other, no, it doesn't weigh anything. It only weighs something in a direction it's moving. So clearly the weight is how an object, a material object, absorbs, okay, energy. So a further argument I'd make is that instead of worrying about energy equals mc squared, what you really should be looking at is the gravitational constant. Because the gravitational constant is really telling you how much energy there is in the universe. It's telling you kind of directly, this is how energy manifests, and this is what will happen to any material object in a gravitational position, and it's always consistent. So it's basically telling you how much energy there is per square foot of space. I mean, the gravitational constant is really the number that's really going to tell you how much energy there is in the universe. All right, so here's the example, I think, of the tennis ball. So yes, a tennis ball standing still versus a tennis ball moving. Now, the argument is neither one of these has energy that you would count if you were going to say E equals mc squared, because the E equals mc squared only has to do with the energy of the matter itself, not the fact that the matter is moving. So there's lots of disagreement about this, because this has to do with the whole, once you gain velocity, they say you gain mass. And this is even an argument attributed to Einstein. So, you know, he's kind of arguing that Einstein argued against this argument. But frankly, I've seen Einstein arguing for it. So that part of the speed limit is based on the idea, okay, that the faster you're moving, the heavier you're getting. And that's why you can't go the speed of light, because you get too heavy. You get infinitely heavy. And therefore you need an infinite amount of energy to push you. When I would simply argue that you can't go the speed of light because you always waste something, and the force can only push you as fast as it's going. So you can never go faster than the thing pushing you. So if the force bits have a maximum speed of the speed of light, you can sort of understand I can never go faster than they can run. Your wagon, let's say you have a wagon, and the only way it can move is that a pusher has to be in constant contact and be pushing you, like if going uphill, for example. And you can only go as fast as the person running behind your cart. Whatever speed he's going is how fast the cart's going to go. And it's the same is true for matter. It can never go faster because, frankly, the matter always reduces the speed that the force can go. It can't go its maximum speed as long as it's pushing matter. And it doesn't matter how many helpers it has, it can certainly get up to a faster and faster speed, right? Say the pushers go 50 miles an hour. Well, I put one pusher on, he gets it up to 10 miles an hour. I put two pushers on, he can get up to 20. Then I get up to 30, I can get up to 40, but I can never go faster than 50. So even with 5 pushers, I still can't go 50 because it's still some mass that they have to push that's going to slow them down. It's sort of a Lorentz transformation thing, but who wants to play with math? All right, so the argument here is that heat does count as extra mass. So a cup of hot coffee weighs more than a cup of cold coffee. Now, I'd argue that if it does, that's only circumstantial, that it doesn't really weigh more. It just means that it can push more because it's vibrating more, but it can't really weigh more. All right, so anyway, I'll play him talking about that a little, just to be somewhat engaged in the video besides just paraphrasing it. I mean, the purpose of the video is just to contrast this standard model mush compared to a theory that really just says, look, it's all mechanical and it's all momentum. And all you need to do is say, if matter's moving, a force had to move it. And so you just look for the force that moved it.
Changed. More energy in the spring, that manifests as more mass. The same thing happens with the coffee. When I added more heat, the internal structure of the molecules changed. In the sense, they're now vibrating more. There's more
right, but why would they be vibrating more? Is because there's more force trapped. But the force doesn't weigh anything. The force isn't like an electron and proton, so it can't collect gravity, it can't collect anything. The only way you can weigh it is to put it on a scale and say, what does gravity do to it? Well, the heat's not going to make it weigh more because the force can't weigh anything. It can't have a weight. Only the matter can have a weight. So that's the catalyst part. The force can't do anything. The force can't act on a force. It can only act on another force with the matter as a conduit between, a converter. So you're not going to be increasing the number of atoms. You're not going to be increasing the number of electrons. You're not going to be increasing the number of things that can collect the force. And unless you increase the number of things that can collect the force, you can't increase its weight. So I'm saying that's just wrong to say it has more mass, because mass is weight. The force by itself can't have a weight. It has to push matter to create weight. Gravity gives you a velocity. Okay, so I've made this argument. Look, we're not sitting here, okay, still. We push into the ground, and obviously the ground pushes us back up. We're obviously not standing still. Our atoms are moving. We can feel them moving. We can feel the differential between one part of our body and the rest of our body. Clearly, our structure is being moved, and it's being moved constantly. It doesn't happen once that, okay, I sit down, and that's the end of it. I don't feel any more pressure. No, it's happening constantly. My body constantly pushes into the earth, and the earth is constantly pushing back. I'm constantly moving, and it's the motion that creates weight. 1 mile an hour of motion. All right, play a little more.
Energy added inside the coffee, and therefore there is manifests as more mass. But when the tennis ball is moving...
So no, it's just not true. When the tennis ball is moving, the simple truth is it will hit a scale and move it more. So it clearly has acquired something that moves scales. So it's acquired pretty much the same thing things acquire in gravity. And so, yes, it doesn't have more mass, but it certainly has more energy. It has a velocity in a direction. Okay, jump ahead a little bit.
This tennis ball now, how would you do it? This tennis ball is moving. You have a weighing scale. How would you do it? Well, one way to do that would be to run along that tennis ball with the exact same speed so that the tennis ball appears to be at rest with you, and then you win.
Yeah, I know, but then we know how much energy we had to use to go the same speed as the tennis ball, so it's a moot. It's moot. This relativity crap really just doesn't work. But anyway, go ahead, fine. You know, tell the story.
Great, but now the tennis ball looks identical to that other stationary tennis ball.
The other stationary tennis ball isn't going to be stationary anymore. You just said, I'm going to start running. Well, what am I going to do? Carry the stationary tennis ball with me? Well, then I know I'm giving it velocity. I can feel myself pushing on it. So I know I'll be giving it the same velocity as the moving tennis ball. So there's no point in saying I can make this comparison by running along with the moving tennis ball, and I can still just look at the one that's not moving. No, the one that's not moving is not going to stay in my frame. So, I mean, that part just didn't make much sense at all.
At the same speed, and look at it from the rest frame, and now calculate all the energy inside it. That's the rest energy.
Okay, so again, he's just trying to make the distinction that somehow motion isn't the energy Einstein was talking about. So something could be moving 500,000 miles an hour, okay, in a direction, a satellite or something, and the E equals mc squared stuff isn't that motion. It's just the dynamics of the atoms it's made out of. And again, I would argue that none of this, this whole conversation is quite moot, okay, if you're not recognizing that this is really about what the energy matter contains when it's in atomic structure. Because when it's not in atomic structure, if they're just free electrons and protons, they don't have any of this energy. Because then they're pretty much stuck in a balanced universe. There's no pressure, there's no, there's nothing pushing them in any particular direction. They're not going to push on a surface of an Earth and then push electrons below them, and those are pushing more electrons, those are pushing more electrons, and increasing the pressure and creating these intense pressures that built nucleuses in the first place. None of that would exist. Then you can't have all this capacity to store energy. So there's no stored energy without the compression device of gravity pushing a bunch of electrons and protons into each other and obliging them to find a configuration that's sustainable, but that has a lot of energy in it. It's a loaded spring. So a nucleus is a loaded spring. It's got a ton of energy because it was built in high pressure. So there's a ton of high pressure, and all you have to do is fracture it a little bit, and all that pressure, all those springs release, and you get these very high-speed particles come flying out. But that's really what Einstein's talking about.
Speed of light for that photon to appear to be at rest. Einstein, can I move at the speed of light with a weighing scale? Einstein says no. Why not? Because according to special relativity, Einstein says, to exert any object to the speed of light, you need to put infinite energy into it.
So he's saying Einstein said that, and then he's going to contradict it and say Einstein said the opposite. So I don't really understand. So he says a lot of things Einstein said. And then he even said the Higgs stuff was Einstein, something about Higgs crap was Einstein. No, it wasn't. Obviously, quarks and Higgs bosons weren't part of a big part of Einstein's physics.
But wait, why does moving at speed of light require infinite energy? Well, you can actually derive this step by step using Einstein's postulates. And what if I told you there was a fun and a free way to actually learn this? Introducing...
Oh, okay, so this is a commercial he has in the middle of his video, really obnoxious and irritating. So it's right in the middle of where he's getting to a rather important point, and, so it's really irritating, that he's put his commercial right in there.
You, me, or donkeys will require infinite energy.
So this idea that you need infinite energy, like I say, the point is that if you do understand it, that the matter doesn't move unless the pusher constantly pushes. If the pusher leaves, the matter just stops. So it only moves while something's pushing it. It doesn't have any motion of its own. It can't go anywhere unless something's pushing it. It's dead. And the only thing that gives it life, gives it motion, is the thing pushing it. And it has no momentum. It can only have force that it's collected. And it loses the force, it instantly stops. There's no, it keeps going, it slows down. No, the force pushes it, period. So if something's moving, it means it's collected more force in the direction it's moving than it's had force in the opposite direction. It's that simple. You can only have force pushing you in one direction in any one of the three dimensions. So I'm either going left and I'm not going right. I'm either going up and I'm not going down, or I'm going forward and I'm not going backward. You can't have competing forces in any direction. You can only have, you have to have more in just the one. So the tendency is going to be for an electron or proton to be always moving in some direction. That is, having force pushing it in some direction. Now, whether it can move in that direction, again, depends on whether it's crashing into a proton. So an electron is already interacting with a proton very close together. It can't go anywhere. And it can't lose any force. So it just keeps pushing on the proton.
To travel at the speed of light. And therefore, I cannot travel at the speed of photon. I can't do the same thing as I'm doing with that tennis ball. Alright?
Well, you couldn't do the tennis ball thing either, so none of that even made any sense. You can't run with the tennis ball and watch the ball that's not moving at the same time. Can't do that. You have to drag the ball that wasn't moving with you, and you're going to feel the fact that you have to apply a force to make that happen.
It's the reason why we say photons are massless.
So they're saying it has no rest mass, and its only energy is in its motion. So therefore it's not covered by E equals mc squared, and therefore it has no energy by E equals mc squared and doesn't count. But obviously it is the source of energy. So as soon as it interacts with matter, it will in fact give the matter energy. So yes, the E equals mc squared is just telling you the matter occupies space, and by occupying space there's a certain amount of energy. So we're back to my argument. The gravitational constant is basically telling you, let's say the number is whatever, 6.23, okay, times 10 to the 23rd or something. Let's just say it's a number. And it's a number in this square meter of space, you could argue. So you just take a square meter of space and you say, this is the number. Okay, there are, this many joules of energy per square meter of space, you could argue, in a sense of that's the average amount of force that's traveling through any square meter of space. And that's pretty much telling you that whenever there's a piece of matter, it's obviously occupying some portion of the space. If it's occupying a portion of the space, that means the force now has less space to be in. If the force has less space to be in, the pressure goes up. See? So in a sense, the matter has energy because it occupies space. But it's the space that the energy is actually in. The pressure is in the vessel. Maybe I'll just draw that real quick. Because it's, sort of basic as an argument of that's just theoretically possible. You could just understand if the universe was a pressurized vessel, that is, you can't get in and out, all right, and you have a certain amount of this stuff, little bits of force, momentum, photons, stuff moving the speed of light. Doesn't matter what you call it, doesn't matter what it is, whether it's particles, waves, whatever. I'm going to say it's vectors of energy, frankly, because that's how it works, okay? So it's little bits moving in straight line vectors through space. And that's the pressure. You can sort of understand that if I put something in here that occupies space, and now this stuff has to bounce off of that, you could get the idea that, yeah, the more of this stuff I put in, the faster and faster the little force bits are going to end up going, in the sense that to get anywhere is less space they have to travel in. So anything that's happening in here, they're going to hit the walls more often, okay, because there's less space for them to travel in. So they have to hit the objects more often, they have to hit the walls more often. So in a sense, you're increasing the pressure. Yeah, I think that's just usable way of saying it. There's a lot to this subject, and I'm really just trying to make a reasonably efficient video. So yeah, you're either going to get it or you're not.
Today we don't use this notion. And I'm like, why? This makes so much sense. Why did we abandon this? Let's calm down a little bit. Einstein says, okay, there's a problem.
So he says this all the time, Einstein says, but he doesn't cite any references for all this stuff Einstein says, so I'm not too sure Einstein said everything he said Einstein said.
What's the problem, Einstein? Well, remember how we said that and when you accelerate an object to speed of light, it will have infinite energy? Yeah. But
okay, so we can't do that. It would take infinite energy, and the argument is because it's getting too heavy to push. But the argument I'm making is it has nothing to do with how heavy it's getting to push. It has to do with the fact that the pushers can't push it faster than they go. So no matter how many of them I put behind the matter always weighs more than nothing. So therefore they're always pushing something, and that means they can't go as fast as they would go if they're pushing nothing. The matter can never weigh nothing. It can go very fast, but it can never weigh nothing to somebody else who shows up to push. So there could be 1,000,000 pushers pushing the matter, and the next guy that shows up to push it, yeah, he'll say, I only have to add a tiny bit of energy, but I can't make it go faster. I can't make it go as fast as we can go, because it's always more mass than zero. And if it's anything more than zero, I have to push slower. I can't go my maximum speed if I carry just even an ounce in my hand. I carry a flea in my hand. I can't run as fast. That's the simple argument.
now, according to this new definition, it should also have infinite mass. And I'm like, cool, so this means in this alternate definition, mass goes to infinity at the speed of light. And I'm cool with that.
So why would you be cool with that, though? Why? For what reason? Why would the mass increase? Why would the electrons or protons somehow get bigger or do something when you don't even believe they're being pushed? You think they've gained their velocity as an independent thing, that there's no constant pusher, that they somehow just are given motion and now they have magical motion. He doesn't think there's a difference between the moving tennis ball and the stationary tennis ball, where I would argue that, of course, the atoms inside the moving ball have been changed. That's why the ball's moving. If I throw a wrench in space, okay, and I have a wrench in the garage, those two wrenches inside, their nucleuses, you could see the difference if we could see inside the nucleuses. We could see that their orientation is different because one does have its heat in a direction.
You can go to infinity at speed of light. Mass goes to infinity at speed of light. I'm cool with that. What's the problem here, Einstein? Well, Einstein says, but photons have mass according to this definition. They have finite mass and they travel at speed of light. They don't have infinite mass. Oh my god. That's the problem. There is a contradiction. On one hand, we are saying...
So it's not a contradiction if you just say, well, but photons aren't matter. I mean, why are we worried about the fact of whether it has a mass? It doesn't push itself. It doesn't get pushed. Its mass has no inertia. Okay, so its mass is never doing anything other than always going the speed of light, and so its mass is always just making momentum, either its own or the momentum of the material electron or proton it's pushing. But that's all. It only converts into momentum. It's always just momentum. Jump ahead a little.
Dear folks, feel free to pause the video. Oh my, what is this? Einstein says exactly. This is the problem with using this viewpoint. It is too confusing. You have to cook up two different kinds of masses, and then you'll have to invent different rules for things that have zero rest mass and things that have non-zero rest mass. It is just too darn confusing. In contrast, Einstein says, look at the other viewpoint. Isn't that simpler? Where you just have one type of mass, and that mass is basically the energy content of the system, and that...
So again, so again, you're talking about a system, and if it's not a system, the electrons and protons are still taking up space, so you could argue they have some average amount of implication in terms of creating a higher amount of energy in the universe. So in a sense, you have to say, it's still real. But this idea that this all comes down to some convenient m times c squared it just has an obvious smell of just a contrivance. There's no relationship, no real relationship. You're just really saying the energy it takes, the quanta of energy in the universe is a tiny thing, okay? The Planck constant, it's a tiny thing. And so that's why you're playing with a gigantic number. Because a lot of tiny things add up to a lot of energy.
That educates us and tells us, remember Mahesh, physics is not about understanding reality. It's actually about creating models to simulate reality.
I don't understand the distinction. Obviously, if we had perfect telescopes and perfect microscopes, then we could just keep looking deeper and deeper, and we could watch everything, and no problem. So I mean, it'd be really nice just to see the real truth, okay? And the only time we have to use models is because we can't see it. So then we have to find some model that produces the same outcome or result. And then ends up being just a simulation, and then you got to worry about whether your simulation is obeying all the right rules or not. But it's the point is what defines a right answer, and that's the tricky part, because obviously you can make a right answer where you start with a bunch of wrong premises.
And sometimes you can have multiple models like you have in front of us. And even though they could be self-consistent, both models are self-consistent, some models are just too darn complicated, and we don't want that. We want a simpler model.
It's desirable, but again, I don't know about what wanting and stuff. It's desirable to have a simple Occam's razor solution, but you still have to measure it by how much evidence there is. So again, you still have to say there has to be some standard that the bulk of evidence is sufficient for a conclusion. And the problem is that getting that evidence for that's a high enough bulk of evidence. And obviously, I would argue that not repeating the Eddington experiment is a huge, it basically just gives the story away that there is no light is bent twice as much by gravity. It's just a nonsense. Kinetic energy is just a nonsense, okay? It was a wrong track. Physics took a long time ago. There's no pull forces. There's no Higgs bosons. There's none of this crap. It's all made out of wrong premises. All of the particle physics is made out of just measuring energy levels and then calling it a particle. So it's really just saying because an electron goes twice as fast, I'm going to call it something else. And it's really not something else. It's just an electron going twice as fast.
That's the reason why we got away with this model. That's why this has become now obsolete. And today we don't talk about moving mass and rest mass. We just talk about mass.
All right, so I don't know who he's talking about because I still hear an awful lot of people talking about rest mass. So that's sort of whatever.
That's it. Just one kind of mass. And we say photons are massless.
And again, what's the point of saying it when they convey momentum? So again, there's no consistency in that logic. So either you understand momentum, it has to be a something, or you should just call the energy what it is, a force, and just say the force is responsible for all motion, and that if something's moving, it's because it contains a force, not because it interacted with a force a million years ago. No, it still has the force. That's why it's still moving.
That's the simpler viewpoint. Wow. That's beautiful. Although we have covered pretty much everything now, I promised you we're going to look at it from all possible angles. So Einstein, I have one last question for you. Under this viewpoint, the simpler viewpoint where we say that mass is the amount of rest energy, in this viewpoint, can photons have mass? And Einstein says, yes. What? It's possible light can have mass if photons travel slower than c.
So this is the part I liked, because now he's going to talk about the fact that let's call c causality. And then we can even understand better that if causality is slower than the speed of light, that is, if when a energy is transferred to matter, the matter is moving less than the speed of light, then we have in fact moved photons slower, okay, merely because they're having to push matter. Now the photons themselves, the force still has its same momentum, but it's obviously not going to travel through space at the same speed. So if I have a photon pushing an electron, if I have a piece of photon, a piece of energy pushing an electron, it's not going to be moving the speed of light anymore. And therefore, it's going to have less energy, okay, in total, because it's not going to get as far as it would have gotten in the universe. So it's going to travel less distance in a certain amount of time, meaning it obviously has less energy. But the matter has the energy. Okay, the missing energy is in the matter. And it's doing something. Just like the heat inside of the Earth, the molten crap is a bunch of energy. It's a bunch of electrons and protons moving. All right, and all that movement came from somewhere. And that's gravity.
That the reason why we have a c? Yes, c is the speed of causality. And so his postulate that nothing can travel faster than the speed of light, or you cannot travel at the speed of light, it actually means you cannot travel at the speed of causality. And, you know...
Well, obviously you can, okay, because the causes are much slower, so you can travel the speed of causality. You can't travel the speed of light. But regardless, the point is that the photons not moving the speed of light are the ones giving matter all of its energy. So if matter has any energy, it only has it when something called a photon or a piece of energy moving the speed of light is pushing matter.
All the different reference frames, it's the speed of causality that stays the same. But then Einstein, why do we talk about speed of light all the time? Well, he says because...
So again, we shouldn't be talking about the speed of light. It should be called the speed of force, because all the forces move at the same speed.
In this case, the light is the one, the photons are the one that are sort of like the carriers of the cause in most cases.
Yes, and they're the carriers of the cause in all cases. So magnetism, electricity, and gravity are all doing the same thing, moving the same maximum speed. And it's all basically the same stuff, and you're really just saying if I give it a different pattern, okay, dot, dot, dot versus dot, 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 it'll have a different effect. So the pattern with which I hit things with the bullets will decide what effect the bullets have on the thing I hit.
And therefore we think that photons travel at the speed of causality. And therefore, everything that applies to causality also applies to photons. But...
So there is no causality unless an electron or matter is being, doing the causing, okay? There can't be an event until a force hits matter. And as soon as force hits matter, it's going less than the speed of light. So causality is always slower than the speed of light.
What if that's not true? What if photons are traveling slightly, ever so slightly slower than the actual speed limit, the speed of causality?
So that's just nonsense. So I don't know where he went. I thought he was going in the right direction. Apparently he's going the opposite direction. So whatever. No, it doesn't work that way. Photons are doing the fastest thing. Causality, okay, the fact that there was an action in the universe that you could detect, you only can detect it because matter's moving, and matter's not going to move faster than the speed of light.
Then all bets are off. Then you can travel at the speed of photon because you are still traveling slower than the speed of causality. You don't need infinite energy anymore. Then you can find photons at rest, and they will have rest energy, and therefore they will have...
So this is just whatever. This is absolute nonsense, right? You're never going to move at the speed of a photon and perceive it at rest. So this is more of this relativity crap. Look, the photon... I'm going half the speed of light. I have a flashlight. I turn the flashlight on. The silly argument is they're saying the beam of light I see the beam of light shoot away at the speed of light. No, I don't. I'm asleep, okay? I'm dead. Because the only way it's going to do that is if I allow time, okay, a tremendous amount of time to pass from my perception. I have to basically make everything drag out twice as long. And the faster I go, the closer I get to the speed of light, the more preposterous this time differential has to get. And so you're really saying that I could look at the rest of the universe and see the universe aged 1 billion years. And then I saw the beam of light leave at the speed of light. So I look out the window, I watch the universe age 1 billion years, and then I see my photon move at the speed of light. Well, obviously, if I saw it, okay, at normal speed, it wouldn't have been going the speed of light away from me. So if I still was aging the same as the rest of the universe was aging, the beam of light would be moving very, very slowly. So that's the bullshit here, is that we're going to play a game that that we think our perception, you're just making up this theory that somehow perception breaks and somehow I don't realize the universe is aging 1 billion years because I'm frozen or something. Why would that be the truth? Why can't I still age as much as the universe? Why can't I look at the universe and see it age the same way I'm aging? That's just as likely to be the truth. I mean, I think the real truth is your physical body disintegrates once you start going really fast. Once you start going really fast, all the atoms fall apart because they're dependent on this equalized pressure. And if you start pushing everything in one direction, the atoms are going to get lopsided. They're going to start to flatten and do other things, and their geometry is going to break down, and they're going to just break. So I don't think you're ever going to get matter anywhere near the speed of light, let alone conscious matter.
Have mass. So does it make sense now why, if photons travel slower than c, they can have mass? So if you put it all together,
This here's a little animated. All right, let's see what he said. I didn't play this last little bit. I like the causality part, but I really don't like this. Causality is faster than the speed of light. No, it isn't.
Put it all together, Einstein. How can we summarize everything that we just learned? And Einstein says we can summarize everything in just 2 sentences. The first one is things traveling at speed less than c should be massive.
That doesn't say anything. There's only 2 things. There's a force, and it always is traveling the speed of light unless it's pushing something. It doesn't have mass because it's pushing. The pushers don't gain mass by pushing. They lose velocity. Okay, that's what happens to them. They lose velocity by pushing. They don't gain mass. And obviously the matter only gains weight in the direction it's moving.
And now it makes sense. Because if you're traveling less than the speed of causality, you can always find them at rest frame. They will have rest energy, and therefore they will have some mass. And secondly...
So whatever, that's just convoluted mush. We're just going to make up a fake new speed of causality that just happens to be faster than the speed of light, and now we can say that photons are moving slower than this fake new speed. I mean, whatever. No sale.
Things traveling at the speed of causality should be massless. That also makes sense, because if you're traveling at the speed of causality, which we...
So again, it's totally nonsensical to say there's some speed of causality that would be faster than the speed of the free force. The force moving freely through space is as fast as you get, and anything that's causing has to be that thing hitting matter, and when it hits matter, it's not going to go faster, it's going to go slower. So that whole thing is just
think photons do, then they will never be able to become at rest, and therefore they should always have 0 mass. That's the reason why we say photons are massless.
So who cares? Again, the point is what you really should be saying is force is responsible for all motion. And it's an actual stuff. And if something's moving, it's because it has more stuff moving this way than moving that way. Or more stuff moving that way than that way. And that's the truth of it. It's a real thing that pushes matter in the universe, and it has to push it constantly. You always have to have an engine running. Okay, let's see what the last little bit was.
Why we say photons are massless? Let me know. This is it from my side. See you.
So again, they don't have mass like matter has mass because they obviously don't require any energy to push them. So, and they can't be pushed by force. Force can't interact with force. Gravity doesn't push on gravity. Gravity doesn't push on light. Light doesn't push on magnets. Magnets doesn't push on this. Force spits. The stuff moving the speed of light does not interact with other stuff moving the speed of light. So force only interacts with matter in any way that could ever be detected. So a force has to hit matter or it's invisible, unperceivable. Okay. So anyway, so we'll see. I mean, it'd be nice if we could get somebody to be interactive on these subjects and argue the specific arguments and see where it goes, but so far no one's willing. So I'll just do my part, and that's all I can do. So I think the part I really want to get into, I guess a little deeper, is just the formation of atomic nucleuses, because that's a really interesting subject. Because frankly, you can't just put one together. You know, I can't just take electrons and protons and just build myself an atomic nucleus. Those things have to be made under very high pressure, and that's the whole point. That's why they have energy, is because they've been put together geometrically under the high pressure, and it's still in there. And that's why you can nuke them. Okay, it's because you can release the high pressure they were built in. That's the real E equals mc squared part. That's the part where you say, this pen can blow up the world. There's enough energy in the atoms, in these nucleuses, that if I can break all the nucleuses, all the arrangements between the protons and the neutrons and the electrons, that inside of here is stored a whole bunch of little photons, and they'll all just blow the thing apart at a very high velocity. All right, enough said, I believe. I'll call it a video. So yeah, it's a little draft. It's a draft physics. It's a draft argument in opposition to what is sort of a standard model defense. Okay, we'll put it that way.